It's my pleasure this evening to be your moderator and to introduce both our presenter and the respondent. Our presenter this evening is Dr. Michael E. Summers, who is professor of planetary science and astronomy at George Mason University. He obtained his bachelor's degrees in physics, math, and Russian language from Murray State University, then a master's in space physics from UT Dallas, and his doctorate in planetary science from California Institute of Technology. He researches the atmospheric composition on planets and exoplanets, which of course are planets outside our solar system. And he also works at the intersections of physics, chemistry, and biology in the evolution of planetary life. He's a co-investigator on the science team of NASA's New Horizons mission to Pluto and to the Kuiper Belt. Very exciting stuff, exciting work, exciting mission. I attended Dr. Summers' talk at the Parliament of the World's Religions back in August, so I have reason to believe that we're in for a real treat this evening, starting right now. So, Dr. Summers, take it away. And while you're getting your slides set up, let me remind people that their questions should go in the Q&A because the chat is disabled. All right, here we go.
Okay, can you see my slides? Okay.
Yep, looks great.
Okay, thank you. Thank you, JD and Maynard, for the introductions. I'm always happy to talk about my favorite planet, emphasis on the last word. I'm changing research fields slightly. I've been studying Pluto for, I guess, the better part of my research career for over 35 years. And I focus mostly on the atmosphere, the chemistry, dynamics, thermal structure, and so on. And on New Horizons, that was my role. I was the lead on the atmospheric modeling. But there's strong connections between the atmosphere and the surface of Pluto and the interior. And that's what I'm trying to flesh out now. And it's a work in progress. And I'm going to share it with you. It's a little bit complex. So what I want to do is to start off by giving you a big picture of what you're going to come away from. A lot of words here. So the central idea is that Pluto probably does have an ocean of liquid water under its surface. Which is astonishing in itself because the surface temperature there is about 37 degrees Kelvin. And yet having room temperature water deep down means that there must be an energy source, which is quite robust. So if Pluto does have an ocean of liquid water, it's going to be joining at least 5 other ocean worlds of the solar system. That would be Europa, Ganymede, and Callisto, the 3 moons of Saturn, of Jupiter, Titan and Enceladus, and perhaps Mimas around Saturn, Triton, Neptune, and then the asteroid Ceres, which probably has a brine ocean. The work I'm doing, which is new, is investigating methane radiolysis within Pluto's ocean that produces complex hydrocarbons as an end product. I'm working with some students on putting together the chemical scheme so that we can understand what we get. And I'm working with an experimentalist at George Mason to do some simulations of this. If that does happen, then that means that if there is a connection between the interior of Pluto and the surface, then the fluids will possibly carry whatever the end products are of the radiolysis to the surface. And we do see evidence of deposits around an ice volcano on Pluto, which I'll show you. And it may be similar to what happens in Europa's surface cracks, where dark material, which is as yet unidentified, has migrated up through the cracks, the numerous hundreds of cracks in Europa's icy crust, which floats on top of a deep ocean. And somehow that material gets to the surface. And so this would have an analog with Europa. in a very strict sense, that could mean that these ocean worlds are habitable. And here it's a very limited very limited perspective on habitability. Just having liquid water, usable energy, not just any kind of energy is usable. Chemical energy, ultraviolet radiation, and even visible radiation is possible. Here I'm going to be looking at radiation, as well as carbon and other elements. So these three things being present is how I'm defining habitability. I'm not talking about civilizations. I'm not talking about higher life forms. I'm just keeping a very simple perspective on this so that I can talk about it with physics and chemistry and not biology. If you look at the discoveries of exoplanets, a large fraction of them are probably ocean worlds, some not just covered with water, but perhaps 80 to 90% of their mass is water, H2O, not necessarily in the phases that we recognize them, but in different high pressure phases. If ocean moons are common, and yet we don't have a clear detection of moons around exoplanets, but they're almost certainly there, and they're common in our solar system. And there are methane and radioactivity present, and those two are also probably a given. Methane is a very common molecule made up of carbon and hydrogen, two of the most abundant elements in the cosmos. And it may mean, and if methane and radiolysis produces hydrocarbons and up to, say, amino acids inside of inside of these ocean worlds, then that could mean that the simple idea of habitability may extend through a large fraction of all known exoplanets. Again, there's a lot of ifs here. We don't know a lot of this. You should think about this as a framework for asking questions and trying to fill in gaps. There's a lot of gaps here. And like I said, a bunch of ifs. So what I'm going to do is I'm going to give you a little bit of background on Pluto, and not so much the New Horizons mission, but what we found at Pluto. I'm going to talk about the surface, the atmosphere, and the interior, the significance for astrobiology, and I'm going to compare Pluto to some of these other ocean worlds in our solar system. And then I've got a few final comments on habitability that I'll share with you. Okay, so this is your 1-minute introduction to solar system astronomy. This is the way you normally see our solar system portrayed. Almost nothing here is to scale. The sun is much larger than it relative to the planets, and it appears here. But you can see that there have the four small rocky, mostly rock and metal planets: Mercury, Venus, Earth, and Mars. You have the gas giants, hydrogen and helium, that make up Jupiter and Saturn. And then there are the ice giants, Uranus and Neptune. But those don't even begin to encompass all the bodies in our solar system. There are millions of asteroids in the asteroid belt, Ceres being the largest. There are perhaps 100,000 Kuiper Belt objects, of which at present Pluto is still the largest member. There are comets that extend out tens of thousands of astronomical units from the sun, and passing an astronomical unit is the average distance between the sun and the Earth. And you have other objects out there that most likely there are planets that have been ejected out there during the formation of the solar system. So in terms of background, Pluto discovered in 1930 by Clyde Tombaugh. He was at Harvard College Observatory comparing images taken on different nights of various areas in the sky. And I'm not sure you could even see Pluto in this image. I'm always amazed at the kind of work these older astronomers did, comparing images like this, looking at one, then the other, one and the other, and looking for differences, which would indicate perhaps motion of an asteroid, comet, or hopefully, in this case, a new planet. And he discovered Pluto, February 18th, 1930. But it's very, very distant. Pluto has a year, which is 248 Earth years. Discovered in 1930, it has not even gone around the sun once since it was discovered. That's how far away it is. Its orbit is unusual. It's tilted and it's eccentric compared to the other solar system orbits. On the left, you can see Saturn, Uranus, and Neptune. Neptune is the one in blue. Pluto's orbit is in, I guess it's a pink color. And it actually intersects the orbit of Neptune in two places, but they never collide. When Pluto is at one intersection, Neptune is at the other one, and vice versa. So it's a little bit unusual. It's what I called earlier, a member of the Kuiper Belt, which is this belt that extends from about 30 AU to about 50 AU from the sun. And it's made up of a lot of very diverse objects. And the ones that we've been able to study are not at all similar to each other. And in terms of size, they're relatively small. This shows the Earth and the Moon, and Pluto is in the lower left. And you can see it's much smaller than our moon, but it's probably as geologically active as, say, Mars is. So it's very different than our moon, which appears almost geologically dead. Not completely, there's things going on inside of it, but not nearly as active as Pluto is. I hope to show it in a few minutes. So in terms of moons in the solar system, Pluto is about comparable to Neptune's Triton moon. Pluto does have a large moon itself, and that's called Charon. It's certainly large enough that gravity makes it round, and it's large enough to retain a lot of heat for geological processes, which I'll talk about in a few minutes. In terms of objects that make up the Kuiper Belt and beyond the orbit of Neptune, we call them trans-Neptunian objects. They're very diverse in terms of shape, in terms of having moons themselves, in terms of color, which represents surface composition, and so on. And Pluto being the largest of that group, and having had a spacecraft mission to it, has given us a lot of information from which we can begin to do comparative studies between Pluto and these other trans-Neptunian objects, mostly with telescopes. It's going to be a long time before we have another mission to Pluto, I suspect. So I'm going to talk about the surface, the atmosphere, and the interior, just as briefly as I can, to give you enough information to understand the overall idea that I'm going to talk about. So the surface, first of all, Pluto's surface is, like I said, very diverse because of its geological activity. It has areas that are extremely bright, that are the largest one shown right here. If you can see the pointer, it is called Sputnik Platinum. And it's made up of nitrogen ice, the stuff you're breathing now, nitrogen gas, which condenses at the surface temperature of Pluto, making a glacier that's about 2 million square kilometers. It's very smooth because it's very recent. There are no asteroid impact craters of any kind on it, which means that it's very young, which that by itself is a mystery. And there are light and dark regions, and we see variations in chemicals all across the surface. When you look very closely at this large glacier, I'll call it a glacier for now, it appears to be bubbling or convecting. And sure enough, there's an energy source underneath it, which is driving that convection. And it also appears to be growing and shrinking occasionally, not quite sure what does that, but it's probably connected to seasonal variations in Pluto's atmosphere. And there also appears to be mountain ranges around it. I'll show you that in a moment. And these are apparently made up of mountains of water ice. Sitting on top of that glacier is a layer of carbon monoxide. There's also methane here. The green is the methane on the planet. This is important. I'm going to be talking about methane in a moment. The methane sublimates into the atmosphere, and chemistry in the atmosphere destroys the methane. So there has to be a source from the inside of Pluto of methane coming up to the surface and replenishing the methane in the atmosphere that is destroyed. So this shows that methane covers a large fraction of the surface of Pluto, even the dark areas, which is significant. If you just spread the map out and look at the diversity, you can see that how the really dark areas down here, Cthulhu Regio, compares to the glacier I showed you, Tomball Regio. There's a difference in reflectivity about a factor of 8. And this dark area is made up, we believe, of complex, probably amorphous carbon compounds, maybe complex polymers that have been radiation or exposed to radiation for billions of years that have stripped off the hydrogens. It'd be nice to have a sample of that because it's very enriched in carbon. There's more organic carbon per square meter in this area than you'll find in the Amazon forest. And it extends over here to the other side as well. It's hard to get a good sense of whether it completely encompasses the planet because the New Horizons mission was a flyby. And so we got really good information on one side and rather poor information on the other side of Pluto. Okay, and as I promised you, I was going to show you a close-up of the mountains right next to Sputnik Planum. These, what appear to be fractured blocks, are mountains about 2 kilometers high and ranging from about 1 to maybe 20 kilometers in length. Each one of these is a fractured piece of a water ice crust that Pluto had that extended over Sputnik Planum, and the convection upwards broke these and pushed them to the side. Now, the convection cells, you can see them as polygons on the right. This is a close-up view of some of the polygons. Some of them look rounded, but they're all have sharp sides to them. Some of them have sharp angles. If you look really close, and I'm not sure you can see it on your monitor, but there are in fact sand dunes on top of these convection cells. And the sand is not silicon dioxide as on Earth. The sand is made up of, again, organic carbon crystals, white ones of some sort. We don't know what that is. If you look at the mountains on the left, and again, those are water ice mountains, there's a reddish hue to them. And that reddish hue is very interesting because when you study I'm sorry, go back. When you look at the highest resolution that we had available to zoom in right on the edge of Sputnik Planum, and the resolution here is about 5 meters, so it's not great. But you can see that some of these blocks that have been broken up have what appear to be layers of this red substance on it, as if the initial ice layer was layered in itself. There's more of it here. We don't have enough information to uniquely identify this red material, but we believe it's another form of carbon, amorphous carbon, not exactly like the kind that we see in Cthulhu Regio, but it fits in this category that we call tholins, THOLINS, which doesn't have a good definition, but the way I'm using the word is just as a group of amorphous carbon compounds, usually long chain polymers. I think in this image, if you look closer, you might be able to see the sand dunes down that are linear features parallel to each other down on this convection cell here. So the sand dunes are actually very new as well, created by blowing crystals, as I showed, as I said. This shows the direction of the motion of the glacier. Now it's moving rather slowly, probably 100 times slower than plate tectonics on the Earth. But you can see how it's pushed against the mountains, and the nitrogen has flowed into the regions between the various mountains up at the top and down here. This little inlet allowed some nitrogen to flow in there. Now, the nitrogen it has a consistency of about that of toothpaste. So you couldn't walk on it. And I mean, if you dropped a rock on it, it might sit there for a few months, but eventually it would sink into the interior. So it's not hard. It does flow, but the fact that it's flowing, the fact that it's convecting again means that there's an energy source inside of Pluto. We haven't identified that energy source. Yes, quite interesting. Here's one more picture of the convection cells at the lower end of Sputnik Planum, right at the bottom of this small image up here. And so that you can see the convection cells have become a little bit more rounded down here. And we believe that these are older convection cells, and they're convection over a thinner layer of nitrogen, but we're not completely sure on that. This is an image of the glacier, the convection cells. You can see it as these white lines outline them. But again, this is a reddish material, which is some flavor of tholin. That's it's draped over the mountains and sometimes layered in the mountains. Over here, that's certainly not a Klingon warship. That's those are a group of a few mountains that are sticking up through the glacier, and they too have this reddish material. Now, it's not clear whether they broke through the glacier or they've been there and the glacier has risen over time to come up the sides of this object or this set of mountain peaks. There were things that none of us ever expected to see on Pluto. Again, it's just incredibly cold. But we found outlines of lakes, and here's one of them. This object down here, which looks like an upside down shark's tooth, was at one time filled with some fluid, and it apparently evaporated or disappeared somehow. And the beach receded until it got down to about this region right here, and then the rest of it froze and made something like a roller rink, I suppose. But a liquid on Pluto flowing, and even though it might have eventually frozen at the low temperatures, means that Pluto once had an environment on the surface, so the liquids were stable. We don't know how long ago that was, but if you look at this, it's smooth, meaning that it has not been around for a long time. If it, and in this case, a long time would be tens of millions of years, because if it had been, it would have a lot of marks due to asteroid impact craters. So there are mysteries. The regions where the surfaces have no impact craters are very young. That suggests a very robust surface processing of some sort. It implies an energy source that drives the resurfacing. And along with other evidence that I'll show you in a moment, this suggests that there's a liquid water ocean inside of Pluto, but there's a lot of work to be done on that just yet. The dark areas, again, are apparently thick deposits of organic compounds, these tholins, and that large region that Cthulhu Regio that had the tholins, the thickness is probably something on the order of 10 meters. So it's a lot of organic carbon. This is a very odd feature, something that is so far is unique to Pluto. We've never seen anything like it. you can see what appear to be blades sticking up out of the ground parallel to each other. And it's tempted to you're tempted to think of these as erosional features. Maybe winds blew from upper left to lower right and eroded away material between each of these blades. The blades themselves are several kilometers high and probably 100 meters to a few hundred meters thick. So they really are a bit like blades. The interesting thing is, or one interesting thing is they're made out of methane. Again, the simplest hydrocarbon, CH4, and it's methane ice. How it became bladed like this, what we call snakeskin terrain, we just don't know as yet. One of what I consider the most important discovery of New Horizons was the ice volcanoes. And the top left shows the first one that was discovered, and and the top right shows the same thing in topography as well. If you look at the bottom, that shows that there's a secondary one that has probably much older than this one up here, and it appears to have sunk back into the surface after it formed. It could be many billions of years old. An ice volcano sounds almost like a contradiction in terms, but the way volcanoes work on Earth, again, very oversimplified, is that you have magma deep underground under enormous pressure, which forces its way up through cracks and fissures. It is released onto the surface either slowly or explosively. And as the magma cools, you get new rock and mountain building. And volcanic mountains are very distinctive, whether they're flattish shield volcanoes or the classical cone-like shape. They're very distinct shapes. Here, it's not quite like this. It's a little more difficult to see the shape of this. I'll show you a computer tilting of this in a moment. But the interesting thing is that there's a lot of dark material that appears to have come out of the interior of Pluto with the material from the inside. Now, what is that material? We believe that it's water. And so what happens on Pluto is that you have an ocean of liquid water deep, perhaps 50 to 100 kilometers deep, under lots of pressure. The water forces its way up through cracks and fissures and then explodes onto the surface, which is exceedingly cold. And then it freezes very, very fast and builds up a volcanic construct as it does that. Here is an image not of the glacier, but of a region close to it. The blue areas are where we believe that the water has come out of the interior much more slowly, so it seeped out through cracks and fissures. Not at all like the explosive cryovolcanism that made up these when they were active. This is also a rather young feature, again, geologically speaking, tens of millions of years or so, because of the lack of, as I said, scars due to asteroid impacts and so on. I'll skip that one, moving on just a little bit. Now, here's a computer is used here to tilt the surface with the topography information that we have. And you can get a look at this, or what we call it's a caldera, essentially, of the volcano. The inside has apparently sunk back down, and that happens with Earth volcanoes often, when the containment vessel, so to speak, underneath it, it releases its volatile onto the surface, and then when it does that, the pressure is released and the surface can sink back down. And that's what we appear to see right there. Now, the interior, what does this mean in terms of this internal ocean of liquid water? We already know, as I said, there's an energy source that is causing the convection and the active geology around the nitrogen glacier. And from that, we can estimate the amount of energy that's coming out of the interior. We can also use the laws of physics to determine from details on the gravitational field of Pluto as the spacecraft flew by it, its total mass. We can use models of hydrostatics to get out the density structure of the interior as a function of radius. And when we put all that together, we find that Pluto has an ice crust that's probably very thick, maybe 100 kilometers thick. And then there's a layer of liquid water below that, and there are probably other phases of water here as well, maybe at the top and the bottom of this internal ocean. And inside of it, there is a core, silicate core, rock core, essentially. But that's a lot of water. That's a hefty ocean there. There's another piece of evidence that suggests that there's an ocean. Now, Sputnik Planum, the glacier itself is like a bowl in the surface that's filled up with nitrogen. And because of that, it has a mass that's density that is different than regions around it. So over time, it's going to orient with respect to the moon, Charon, that orbits rather close to Pluto. It's going to orient so that the glacier is always opposite or focused towards the moon Charon. And you can get a sense of that from this animation. Pluto actually rotates once every time Charon goes around Pluto. So, if you're on Pluto, you're going to always see the same side of Charon. Doesn't matter where you are, you're always going to see the same side of that. Just like the way we are on Earth, we look at the moon, we always see the same side of the moon. But for Pluto, it's doubly locked, or doubly tidally locked, I guess is the way to say it. If you were on Charon, looking back at Pluto, you would see the same side all the time. So it's like the locked in step as they rotate about each other. And as I said, that can be used to set constraints on the internal structure, on the extent of the ocean, and in particular on the thickness of the ocean. And this is a profile that comes out of that modeling. I didn't do this. This was done by another group. You've got the bowl of the nitrogen ice, a crust of water ice, what we call a clathrate, which is a crystal cage of water molecules. And then there's the subsurface ocean, which appears to be thicker, it must be thicker to be in hydrostatic balance, right underneath the glacier, which is always oriented in the same way towards Charon, and then the rocky core underneath it. Again, the point of all this is that it has an internal ocean, and that internal ocean requires an energy source to keep it liquid, because if it did not have that, it should have frozen solid, probably within a few 100 million years after it formed, if not even before that. And Pluto is as old as our solar system, 4.56 billion years old. So it should have frozen solid long, long ago. So there's an energy source which has not been identified that must be keeping it warm. And that energy source is probably the same one that's causing the convective and the active geology of Sputnik Planum. Now, my role on the mission, as I said, was to lead the modeling of the atmosphere. In particular, I worked on the chemistry and the thermal structure, the ionosphere, and the dynamics of the atmosphere. This is an image that kind of surprised us. It's taken by the spacecraft after sunset. In other words, the sun is over the horizon here, but the sun is shining on the atmosphere a bit above at high altitude here. This is probably 200 kilometers or so, maybe a little bit more. And the atmosphere has particles in it, haze particles. And there's so many, and they're so forward scattering that it lights up the topography underneath it. If it didn't, this would all be black. We wouldn't have enough light, reflected light, to make an image. We'd see the haze layers, but we wouldn't be able to see this. If you look at the haze layers, you see that some layers are thick, some layers are thin, but they all tend to be spaced about the same thickness, about 10 kilometers. We've never seen anything like this in planetary sciences. Nowhere else in the solar system do you see haze layers that are so fixed and are stable for 1,000 kilometers as you go around the planet. In my work, I did predict that there would be haze and haze layers, or a haze layer, one haze layer. This one you can see just above the surface here. I did predict that in my models, but as far as I'm aware, no one predicted these layers, which we still do not understand clearly, although we've got some ideas that hold promise for this. This is the bottom edge of Sputnik Planum, and these again are water ice mountains, basically water ice cubes, and here is the cryovolcano. I threw this in just largely because it's very revealing when you study it. You can see mountains sticking up here on the horizon. See the haze layers very distinctly, and you can see the haze layer going over the mountain and not being perturbed by the mountain. If it was dynamically moving horizontally, you would expect some sort of movement over or perhaps even around the mountain, but we see nothing like that. It's just fixed at a solid, at a given altitude. Again, not quite explained yet. Very weird. Sorry about the technical aspect of this, but I wanted to show you what we found about the composition of the atmosphere. It's mostly nitrogen, like our atmosphere is mostly nitrogen. The atmosphere of Titan is mostly nitrogen, and it has maybe 1 or 2% of methane in it. And Pluto has low gravity compared to like the Earth or the Earth's moon. And so because of its low gravity, the atmosphere sort of puffed out very, very far. To go to the upper limit of the atmosphere, what we call the exobase, you have to go about 1 Pluto radius above the surface. And so there's atmospheric components, chemicals that extend from the surface all the way up to the very top of the atmosphere, where the atmosphere is sort of evaporating off into space. And here just it shows the distribution along the line of sight from the spacecraft to Earth of some of these chemicals. The black is molecular nitrogen. This color here, which I think is pink, is methane. And then down here you have higher hydrocarbons, ethane, acetylene, ethylene. And then down here you have the signature of the haze itself. The point being that there's methane in the atmosphere, but it's being chemically converted into these other chemicals, and that process we understand pretty well. And it's solar or ultraviolet light from the sun hits methane and breaks it up, and that triggers the formation of larger, heavier, more complex hydrocarbons. And this is something that we saw on Titan, Saturn's large moon, when we had the Cassini spacecraft there. On Pluto, we think it's the highest energy photons, probably not just ultraviolet, but extreme ultraviolet, producing the ionosphere. And as the molecules get bigger, they tend to stick to each other and grow into tiny little haze particles. So you get a complex sequence of events. You break up the nitrogen CH4 initially into CH3, which is a radical, and hydrogen atom. And the hydrogen atom is light, and it will probably escape the top of the atmosphere. The CH3 can react with itself or another molecule in the atmosphere to create a higher order hydrocarbon, a C2 hydrocarbon, or C3 hydrocarbon, meaning the 3 carbons along with other hydrogen, nitrogen, or oxygen atoms bounded. So very easily you can get sunlight breaking up methane and triggering the formation of things all the way up to benzene rings, and even beyond that, things that we can't really predict too well. Very large particles. which then fall because of they're heavier than the air around it, and they fall and they grow as they fall, and eventually they're going to hit the surface, and this will be a very complex mix of organic molecules, and as they fall, they're also exposed to extreme ultraviolet radiation and charged particle radiation, which takes off hydrogen atoms from this ball of organic material. So it becomes enriched in carbon and depleted in hydrogen. And by the time it gets to the surface, it's what we call tholins. And the same type of process worked on Titan. And you get when it falls to the surface, you get these very dark black areas. And this continues to happen over billions of years. And over 4.5 billion years, you would get a layer of this tholin material that would be on the order of 15 to 20 meters thick. Very conservatively, 10 meters, more probable 15 meters thick of organic carbon, an astonishing result. I don't want to go into the big picture of Pluto. It's clear that there's methane and nitrogen coming out of the interior to replenish the methane and nitrogen that either escapes or is chemically converted to other things. We know that there are winds that blow the methane and other ices around on the planet. There's complex heating and cooling processes going on by radiation. There's the particle formation, condensation and growth, sedimentation in the atmosphere. And then you also have different compounds settling on the surface by the time it gets there. It's a, most of the material is what we call tholin. Okay, now I want to talk about a couple of other objects in the solar system first as a comparison and to show you the astrobiological significance of Pluto. The large moon of Saturn, Titan, is basically a natural organic laboratory. Again, a nitrogen atmosphere, a thick nitrogen atmosphere. It's in fact about 1.5 times the pressure where you're in the room wherever you are right now. 1.5 times sea level pressure at the reference radius of Titan. And inside this nitrogen atmosphere, you have about 5% methane. It's somewhat similar to Pluto. Although in Pluto, it was 1 to 3%. Here, it's about 5%. But the overall pressure is much, much higher. So you have a lot more methane in the atmosphere. But the methane is broken up here probably by magnetospheric ions or electrons that hit the upper atmosphere as Saturn's magnetosphere, it rotates with the planet. And the ions that are stuck to the field lines on that rotation hit Titan going at very fast speeds and giving them a lot of energy. And they can ionize and they can break apart the methane, similar to what happens on Pluto. And a similar chain of reactions happen. They form complex organics, which tend to stick together and grow and fall. And eventually they'll hit the surface and they'll create even lakes here. You can see lakes, sunlight is glinting off of some of those lakes that we see. Here, it's not a solid, though it's something that's more liquid and probably more like ethane or acetylene, something like that, maybe with a methane mix. Here's a high resolution image of the beach areas around that sea. The black is the sea, the gold is the land. And so you can see like an archipelago and peninsulas. The odd thing is that over time, some of the islands appear to sink and then rebound. They sink and then rebound. A very strange effect, like a cork, an island that floats and then sinks sequentially. Tholin production on Titan, very much like on Pluto, just to say that. We also find complex organics in meteorites, just to say that in passing, we even find amino acids in some meteorites when we can convince ourselves that it's not due to contamination. And then the similar type process has happened on Earth. The early Earth had an atmosphere. Initially, it was probably steam, or at first it might have been a vaporized rock, but it had a steam atmosphere for a while, and then probably a thick carbon dioxide atmosphere after a few 100 million years. But it also must have had a lot of methane present, because there was methane and hydrogen cyanide and other things in the materials from which the Earth formed. And one of the common ways that the early atmospheres are studied is through what we call a Miller-Urey experiment, a very famous experiment that was done in 1953 by Harold Miller and his student working at the University of Chicago. And what they did is a very simple thing. They got a very pristine, clean containment vessel and put in water, methane, ammonia, and subjected that to electrical charge to simulate lightning. Let it go on for a few weeks, and then you get the residue out, and you run it through a GCMS, gas chromatograph mass spectrometer, to find out what it is. And you find out it's complex organics, all the way up to a wide range of amino acids. The products, the chemical products, are a strong function of what you assume for the initial gas, the hydrogen, the methane and CO2 and so on. But the Earth was different than Titan, which is different than Pluto, but the same kind of process, an energetic breakup of the methane molecule triggered the formation of complex organics. So that's nothing new. I mean, this has been done many, many times. And so, breaking up methane, which is very common, to trigger the formation of complex organics is very well known. And the specific products depend upon the atmospheric or the liquid that you start with. Now, the haze layers on Pluto are produced in a very similar manner. And we also see, as I noted earlier, a reddish residue around the ice mountains around the cryovolcano that appear to have come up from the interior. So how do you create tholins inside of Pluto? And that's the question I've been looking at. And it turns out that if you're in a liquid, there are a few differences in the chemistry. I probably shouldn't show this. This is really too complicated. But the net result always works out about the same way. Now, again, the specific products depend upon the starting atmospheric mix. But the question I'm after is can radioactivity do the same thing in methane that's in this internal ocean on Pluto? Can it produce complex hydrocarbons? What will be their nature, their chemical structure, and so on. There are a lot of questions that haven't really been addressed before. It's sort of like a Miller-Urey experiment for an internal ocean. And I have 3 students working with me on this to do some theory, and I'm collaborating with a colleague of mine at George Mason to simulate this in the laboratory. Again, students are helping with this. And it's just a Miller-Urey experiment. That's, just from a textbook. But it's going to be using a liquid in the containment vessel, mostly water with methane as a minor component, and the high energy source that will break apart the methane is radioactivity. And we're going to try a couple of different types of radioactive materials. So that's the goal of the research. Now, I'm going to talk about habitability a bit, and this is where it gets a little bit speculative. But I want to make sure that it's clear that I'm talking about when I say life, I'm talking about Earth life. carbon-based. You know, it has characteristics, life has characteristics that we know. These are general characteristics. You can find exceptions to metabolism. You know, fire metabolizes, but we don't call it alive. Crystals reproduce, but we don't call those alive. You know, my thermostat responds to stimuli, but I don't think that's alive. I hope it's not. But on Earth, we know that all life requires a source of raw materials, in particular carbon, again, usable energy and liquid water. Every form of life on Earth that we know of requires liquid water, at least at some point in its life cycle. Many things like tardigrades can be dried out for weeks, but you put water on them and they are reanimated. And now I want to compare with some other oceans that are known for our solar system. I just show this picture because we'll be talking about the moons of Jupiter, and I just wanted to emphasize how big Jupiter is. And this is to scale. There are storms in Jupiter's atmosphere bigger than the Earth, on top of which this whole planet rotates every 10 hours or so. It has a huge magnetic field, 10,000 times as strong as that on the Earth. And that magnetic field and its gravitational field extend into space, and it affects the moons that orbit Jupiter. Now, there are over, I believe, 80 moons now that are known for Jupiter. All but 4 of them are captured asteroids of one sort or another, and small. There are 4 that are very large, Europa, Ganymede, and Callisto. And these were discovered by Galileo. He was able to see them and map the positions night after night with a very small, crude telescope. And you can do it almost with binoculars if it's a good pair of binoculars. And this is just a piece that I copied from his notebook, just to show that he saw 4 of them, and quite an amazing thing to discover these 4 objects. And what I want to talk about is the impact of Jupiter's strong gravitational field and its magnetic field on these moons. Now, the moons are also tidally locked into a pattern akin to what the Earth and the moon is, and Pluto and Charon is. But here it's a little bit more complicated. Every time Ganymede goes around 4 times, Europa goes around twice, and Io goes around once. Did I say that right? Yeah. No. Yeah. Ganymede has a period 4 times that of Io, or twice that of Europa. And so every time that these moons are lined up with Jupiter, there's a gravitational stress on them. Jupiter's always pulling towards the planet, plus or minus a little bit of an angle there. Yet the moons are almost always pulling away from Jupiter when they're close to each other. So you can have Io that is pulled very strongly towards Jupiter, and when they line up, that Europa and Ganymede can pull it away. So you get stretching and relaxing, which is just friction. And the amplitude tides are enormous. They can be as much as 100 meters. Think about the tides at the eastern shore, a few meters if you have a high tide period. And yet here you've got a solid body that's causing the planet to stretch and relax for Io. And that releases so much frictional energy that the moon is basically a molten ball, or a ball of magma. It's the most volcanically active object in our solar system, and you can see this in the images of it. It's on the surface. Every black spot here is basically a volcanic feature. Almost all of them are active at any given time. The white is sulfur dioxide ice. The yellow is sulfur allotrophs. Upper right is a picture of a fissure eruption. Lower right is a recent picture from Juno showing an eruption there on the edge. There's a Juno infrared image there showing that every spot there that's lit is where there's an active either volcano or a pool of magma. The New Horizons spacecraft went by Jupiter to slingshot on its way to Pluto. We stole a little bit of Jupiter's momentum, which got us to Pluto 2 years early. And we were able to take a picture of one of the plumes going off when we went through the Jupiter system. And that's about 250 kilometers high, about 600 kilometers in width. That's the plume of material that's being thrown up. A very, very energetic planet just produced by heat, frictional heat, tidal dissipation. Now, Europa, the next moon out, is very, very different, or at least at first blush it is. It's an ice crust ranging in thickness from maybe a few kilometers up to 50 kilometers on top of an ocean of liquid water, on top of a rocky silicate mantle, and then a core, which is probably metallic of some sort. But yet it too is being stretched and heated, but not nearly as much as Io is. Here's one of the plumes that was seen with the Hubble Space Telescope. It's really hard to get images of this from the Earth, but that's a plume of water shooting out of Europa. Again, to this tidal heating. I've been studying Io since I was a graduate student. I did my PhD thesis on it. And the energy is just phenomenal. But it's much lower at Europa, but still enough to keep the ocean molten. You probably have volcanoes at the bottom of an ocean that's hot due to these volcanoes, and that's due to the stretching inside of it. But you have a water ocean on top of it, and then an ice crust, as I said, varying in thickness with cracks, many, many cracks, hundreds of cracks in the surface through which the plumes arise. A similar type thing happens on the moons of Saturn, or at least some of the moons of Saturn. Titan, I've already shown you. The Cassini-Huygens probe that landed on the surface showed dozens of complex hydrocarbons, again, produced through the Miller-Urey type atmospheric process. We don't call it Miller-Urey in the atmosphere, but it's essentially the same type of thing. Even the small moon Enceladus has an internal ocean of liquid water. And it's just a few hundred kilometers across, but yet there's an ocean of liquid water, which is heated at the bottom by tidal energy, like Titan, like Io, Ganymede, and Callisto. Tidal heating gives you thermal energy, which keeps the oceans warm. In the case of Enceladus, it creates the bright, highly forward-scattering particles of ice that are seen here backlit by the sun, of plumes of water being shot into space. It's very hot, and these plumes have not just water, but methane and carbon oxide and carbon dioxide, simple organics, complex organics, salts, molecular hydrogen, many of the things you would find around hydrothermal vents in the deep oceans on Earth. So you've got several clear ocean worlds that don't have water on the surface of the planets, but there's a thick ocean of water there. If you compare them, here's the total volume of water on the Earth, about 1.3 billion cubic kilometers. Europa has at least that much, probably more like 2 to 3 times that. Titan has 13 times the amount of liquid water that the Earth has. Callisto, 12 to 14. Ganymede, there is some uncertainty, but it's probably at the high end. And even Enceladus has a tenth of the water that the Earth has in all of its oceans combined. The Earth is actually one of the drier places in our solar system. And this changes the idea, the concept of a habitable zone. The habitable zone is sort of classically defined as the range of distances from a star where you can have liquid water stable on the surface of a planet. And this has been called the habitable zone, the Goldilocks zone, and it has other names as well. But the idea is that Earth is the only planet in our solar system that is in this habitable zone. Mars is too far out, water is frozen, Venus is too far in, water would vaporize and then ultimately be lost from Venus. But we've got these subsurface oceans, which also are liquid and stable and have usable energy and satisfy the same kind of conditions. They're just not exposed to the surface. It changes the idea substantially. Now, the idea of a classical habitable zone is still useful to prioritize all the different planets we see out there. Because if a planet is in the Goldilocks zone, that makes it probably even more likely to have water than others. But the idea is that Venus is too hot, Mars is too cold, and the Earth is just right. Whereas the reality is that there are as many as 9 planets and moons in our solar system that have an ocean of liquid water. Now, Mars doesn't have an ocean, but it has underground lakes. Titan, I mentioned a natural organic laboratory in the atmosphere that sits on top of an ice crust that floats on an ocean. Europa, its ocean. Enceladus, its ocean. Pluto, its ocean. We've got Ganymede and Callisto, which I didn't have time to talk about. The asteroid Ceres has a crust of rock and ice sitting on top of a very salty ocean. It's probably 30% salt or so more like brine than water. But it's in a range of salinity that there are some organisms on Earth that would thrive there. Some acidophiles, halophiles, and even tardigrades apparently can live in that environment. So that too is habitable in a limited sense. Neptune's moon Triton is a candidate, but we don't know enough about it yet. We've got some interesting images and observations from the Voyager flyby, but we've got much more work to do to know about that one. So I'm running out of time, so just a few final comments, and then I'll wrap up. So as of today, 5,660 known exoplanets, thousands more candidates, and there's a discovery rate of about 2 per day. Just huge numbers of these out there. What are they like? Well, they're highly varied. This is an older figure, but the commonalities are there. There are hot Jupiters. Some of the first exoplanets detected are Jupiter-like, very massive planets, very close to their central star. And then there are cold gas giants like Jupiter and Saturn. There are Earth-like planets that are so close to the central star that they're lava worlds, and then there are lots of rocky planets at higher orbital periods, which means a further distance from the planet. I forgot to say that the axis here on the left is the physical size relative to the Earth. 1 would be 1 Earth radius, 4 would be 4 times Earth radius, and so on. And down here is their orbital period. 1 Earth day, 10 Earth days, and the Earth would be out here around 360. You can see there's a big region here that we don't have any. It's not because they're not there. They're probably huge numbers on there, but our limited technology allows us to detect very few planets that are Earth size or smaller, especially if they're far from the central star. There are a few that have been detected, but not many. So in addition to lava worlds and rocky planets, and probably many, many more of these out there, there are the ocean worlds and ice giants, which I think are just incredibly fascinating. So, the requirements for life, and this is a very simple picture, okay? Carbon, liquid water, usable energy are commonplace. Clearly, an ecosystem takes more than that. I understand that. I'm just trying to get a sense of the habitability sort of starting points in our universe. We find these requirements are met in many places in our solar system, even asteroids, which to me is very astonishing. It means that there are other habitable places in our solar system. If life isn't there, which I have no reason to think that it is, we could transplant life there. Simple life, probably the most dominant form of life on Earth is extremophiles. We could transplant them there, and they would be quite happy as bacteria could be, I guess. And so from that perspective, there are, other planets, moons, and asteroids that are habitable. And if moons are common around other exoplanets, in other star systems, other planetary systems, which our formation models suggest that moons are common, then every system probably has, on average, a habitable place around it, which is just astonishing. Again, a lot of ifs here. I'm trying to build a framework for thinking about these ideas. And there's also the implication that if the energy is due to tidal dissipation, then you could have that in the interstellar medium. Jupiter and its moons don't depend upon sunlight. All their energy comes from the interior. Jupiter generates more energy by about a factor of 3 than it receives from the sun. If it was in the interstellar medium, almost nothing would change. You just wouldn't see reflected light. The moons would still orbit, and there'd still be the tidal dissipation. Same thing with Saturn. Same thing with Pluto. If there's a source of energy inside of a planet, like radioactivity, then that would continue as long as the radioactivity survived. So what I'm saying is that the real habitable zone can extend far out away from a planet. It may have a well-defined inner boundary at which the temperatures are too high for organic molecules to exist. But the outer boundary depends on whether or not the planet has an internal energy source. I think I don't have time for that. And this is from an article by Sarah Seeger, where she emphasized that if you have an internal energy source, then you could have a planet that's habitable, basically with an upside down greenhouse effect that could be anywhere in the interstellar medium, far away from the central stars. I just want to end with big numbers. I always loved big numbers. Ever since I was a kid, I loved big numbers. 300 billion stars in our galaxy, plus or minus a bit. Just some other big numbers. This tiny little piece of the sky, about the size of a grain of rice held at arm's length, held 50,000 galaxies. This is a deep field from the James Webb. This image by itself helped me convince one student that there must be a God. If you look at some comparison numbers, it gets kind of interesting. The combined number of heartbeats of all the people that ever lived on Earth can be roughly estimated. It's not going to be accurate, but you can estimate. It's about 1 in 20 zeros. The combined number of grains of sand on all the beaches on Earth, about 1 in 22 zeros. If you estimate the number of Earth-type, rocky metallic, potentially habitable, that have liquid water either on the surface or inside of them, including moons, the potentially habitable planets in the observable universe is 1 in 24 zeros, which means for every single heartbeat of every person that's ever lived, there are 10,000 Earth-like planets that are potentially habitable. And this is based upon what we know now, which is sort of a lower limit to what's out there. And if you look at it another way, for every star, there are on average 1 to 3 large planets, on average 2 to 4 large moons, probably dozens of smaller round moons. And for every star, there are on average 1 to 3 habitable locations. Again, this is built on a lot of ifs, and there are places that are missing in this framework, but this is where I'm working right now. This is my interest. So anyhow, I'm going to stop sharing, and I'm willing to take questions as long as my voice holds out.
Thank you very much. That was fascinating. We do have some questions, but first we're going to take a few minutes to introduce our respondent this evening, who will have some comments, and we'll throw out the first question to get the conversation started. Our respondent is Christopher J. Corbally. He's a Jesuit priest and astronomer with the Vatican Observatory in Tucson, Arizona, where he serves as vice director and liaison to its headquarters at Castel Gandolfo, Italy. He's an adjunct associate astronomer at the Department of Astronomy at the University of Arizona, and ministers to a wide variety of Catholics, including Native Americans, in Tucson. He was the president of IRAS from 1999 to 2002 and is the co-founder of the Human Sentience Project. As he likes to quip, old astronomers don't die, they just fade into the ionosphere. So, Dr. Corbally, your response, you can turn on your camera and mic.
Michael, thanks awfully. A wonderful, introduction to the wonders of Pluto and also other icy moons like that. Really wonderful. I get your enthusiasm and excitement. I also got it from a colleague of yours on the New Horizons team. Todd Lauer is just across the road at the National Observatory. And during the Todd Lauer, who's a cosmologist and galaxy person, had an idea about how to enhance the imaging that New Horizons was giving. And so that's how he, a cosmologist and galaxy person, found himself on a planetary expedition. And but he's a wonderful scientist. He, while the New Horizons was going on, well, at least while the pictures were coming back, while it was passing Pluto, he was here at the, at Stewart Observatory, where Batting Observatory is hosted. And so I could catch the excitement from him as he said, look at this image, we just got that. Oh, it is absolutely wonderful. So it's great to have Todd. And I enjoyed very much being on a local radio program with him, and we had a great chat and things. So that's one connection I have with Pluto. My other one would be, well, it goes back a bit to 2006, August, when the International Astronomical Union, had a resolution. I was chair of the resolutions committee, as it was, as it's called. It was my job to put forward the resolution. It took an awful lot to get the right resolution, and you know about it. And I'm delighted that actually, right when I proposed the resolution, somebody stole my voting card, so don't blame me, okay, for what happened with Pluto. But I think that it's much better to be, rather than the runt of the planets, the chief of the dwarfs. So I'm happy. And like any scientific definition, Pluto and what's a planet will change. But anyway, that's where we have it at the moment. The other connection, so the third one is, I'm a little bit puzzled when you said Cloud Tombaugh discovered it in Harvard. I thought it was up at Flagstaff at the Lowell Observatory.
You're right. You're right. I'm sorry. You are absolutely right.
Ah, lovely. Because now, I don't know whether you know, about a month, just a few weeks ago, Pluto was declared Arizona's planet. So anyway, wonderful connection there. Great things to have. Let me do just as far as a kind of a question. Let me, if I may just share this. I have a wonderful colleague, Margaret Rappaport, with whom I've been working for a little while. And, we've been, having considered human origins, we then wondered about humans in space. What's the next step? And so these are a couple of papers in Theology and Science, one from last year and one that's about to come out in Theology and Science for next year. And I think actually they both directly concern what you're talking about, because this is wonderful. This is great science. This is great speculation in a way, hypothesis. It's how do we really know whether there are these, wonderful ways of alternate life, other life than we know. It's a beautiful question. How are we going to know it? And in back of my mind is somebody a geologist saying, look, if we could only have 2 or 3 geologists land on Mars for a long weekend, give them a little vacation and send them to Mars for a long weekend, we could learn much more about Mars than the current landers do. And maybe we could learn, if the biologist, we could learn if there's life there. So that human element in explanation, New Horizons was and is a wonderful machine. Todd Lauer is still doing experiments with it on the cosmic optical background. It's a wonderful machine, but maybe we really get to know these things, need humans there. These papers discuss humans in space, and how we need to treat everything with care, and concern. So that's what I was kind of in the back of my mind wondering, the what's the next step? Is it to send another probe out to Pluto, or is it eventually is it humans that are going to go to I suppose the first one might be around Jupiter, so Ganymede or Europa, and then maybe think of Titan, a wonderful source in Enceladus. Yes, what's the best way?
Well, of course, that's a difficult question. Every situation, every target in our solar system is unique. And as you know, human spaceflight is very expensive and very dangerous. So in a culture of limited resources, I mean, once we become a non-scarcity civilization or post-scarcity civilization, we can do things like that. But now we can't. It's very hard to send something that is as far away that it takes a light signal 4.5 hours to get back to Earth. That's how far away Pluto is. And it would take a huge spacecraft with a lot of mass, a lot of systems to take humans there. I'm all excited about going back to the moon with the Artemis program, and I think it's time we do that to look at the distribution of water ice at the poles on the moon. But sending people to Mars, I think is right now it's premature. We need to learn a lot more about humans in space. We learned a lot about how space and of course low gravity affects human physiology by studying the astronauts and the cosmonauts on the International Space Station. But even they, who set records of more than a year in space, haven't stayed in space as long as it would take to go to Mars and come back. And so we just don't know enough. I mean, for instance, how do you do CPR in space? There's not a person on Earth, as far as I know, that knows how to do that. You would think, if you've taken a course in CPR, you would think you just put them against a bulkhead and do compressions. But it doesn't work that way in zero G. Your blood flow is completely different. And as far as I can tell, there's no clear answer to how you do CPR in space, and it's going to be needed to do. How do you?
I'm going to stop you there because we have far more questions than we have time left. Fascinating conversation. It's been really good. I want to just cover a few of these, and then we're going to have to come to a close. Let's see. The first question comes from Paul, who asks, compared to Pluto, why is nearby Mars so barren? And I'm not quite sure what he's getting at there. Do you have thoughts about that?
I'm not at all convinced that Mars is barren. There's methane gas coming out of the subsurface that is very plausibly due to bacteria, methanogens. It's been known for over 2.5 decades that methanogens can live in a simulated Martian environment in the laboratory. And before the methane was detected, a student of mine and I wrote a paper where we predicted that if methane was there, it would be an indicator of subsurface life, even if you couldn't detect the life directly. But you have to have more than just the methane. You have to look at the D/H ratio and the isotopes of carbon and 12 and 13 to really identify life. But there's a lot of methane coming out, and it's somehow synchronized with the seas and synchronized with oxygen coming out of the subsurface too. And it's coming out of a very particular region on Mars. We also know that Mars has subsurface lakes about a kilometer down. There are lakes, probably very salty lakes, but there probably are lakes there. There's probably a huge amount of permafrost underground. We don't know what's under the surface on Mars. The
So
surface,
it
the
appears
surface
barren.
yeah. The surface appears hostile because there's no ozone layer to shield it from ultraviolet radiation, and the atmosphere naturally makes hydrogen peroxide, which settles onto the top 2 or 3 centimeters and essentially sterilizes that. But you go down more than a few centimeters, we don't know what's there. If
There could be a lot going on under there. Yeah.
life originated when Mars was younger, and it migrated underground as the water dried up, and the water is probably, a lot of the water is probably still there underground as permafrost, maybe even deep, kilometers deep. And so you could have an underground ecosystem there. I don't have evidence for that, but we haven't ruled it out.
Okay. Gail asks, what she wrote is, the knowledge you presented is truly fascinating. Thanks for your work. You used mystery and don't know a fair number of times during the presentation. Can you speak to the knowledge as wisdom or meaning? Do you see wisdom emerging as well? I think what she's getting at is that relationship between what we're learning about these, about exoplanets in general, and wisdom.
Yeah.
Have thoughts about that?
Yeah. Well, again, you're probably cutting me off, but yeah.
Keep it short.
The simple thing is that I'm a Christian. I'm a believer. I believe that the universe was created by God. And I see God as an artist, as a symphonic conductor of a majestic, symphony. And when I look at the universe, I'm in awe. It's just a natural feeling I think that we get when, like Psalm 19 says, heavens declare the glory of God. Day to day pour forth speech, and night to night reveals knowledge. And that word knowledge there has the same root from which we get the word science. So is that a connection between science and wisdom? I suspect that it is, although it's hard to articulate that. But as I said earlier, I have one student who I was able to convince that there must be a God by showing him one image from James Webb. So he has gone from knowledge to perhaps a little bit more wisdom as well. Again, hard to articulate. I can't quantify it. It's not scientific. And I'm not sure you could answer this question in a scientific way, but I believe the answer is yes.
Well, thank you. We have several more really great questions, but we are out of time. So again, thank you so much for your presentation, and go ahead, Mia.
If you have another one, why don't you have at least one more?
I would like to ask Greg Derry's question. He asked, is it a probable speculation that there might be something similar to thermal vents in some of these internal subsurface oceans? And I think some of your diagrams answered that.
Yeah, absolutely. The deep ocean of Europa, it would probably look very much like black smokers that we have in the deep oceans on Earth. Similar type things would hold on Enceladus. I don't know about Titan, but those two in particular would be driven by, or the water would be heated by volcanism. So you would expect something like a mid-ocean ridge type chemical system where you have heat and water, hot water, coming out of a vent, and a lot of chemicals that are dissolved in that water because it's been in contact with the rocks that it has dissolved on its way up. And it would be a rich chemical environment from which you could, do all sorts of interesting chemistry. So the universe could do, trillions of natural experiments on the origin of life around those events. And so it's, yeah, absolutely. And that's one of the sort of the ways we think about the base of these oceans. So good question.
That possibility is really exciting to me personally. So,
Very good.
cool.
Well, thank you.
Well, thank you for your presentation. I learned a lot, and I imagine everyone else tonight here did too.